Hi, my name is Manish Gupta, and in this video, I'm going to talk about query-dependent video representation for these two interesting problems, moment retrieval and highlight detection. Okay, so let's get started. Let's first understand what is video moment retrieval and highlight detection, these two problems. Okay, so given a particular video given a particular video and a particular text query. So for example, given this video and some frames are shown here, and there's a text query, man with curly hair speaks directly to camera. The moment retrieval kind of a task tries to localize the moment relevant to the given text description. So this moment is relevant. The last frame is also relevant because it shows a man with curly hair speaking directly to the camera, right? Now, similarly, if you look at the other query, kids exercise in front of parked cars. Now, there are no kids exercising in front of parked cars in that census, and therefore, these frames are sort of, or rather, this video is not really relevant for this query at all. Okay? So more formally, the moment retrieval problem is essentially about localizing the moment relevant to the given text description, and highlight detection problem is to measure the clip-wise importance level of the given video. Okay. So here you see outputs from two different systems. One is called as moment detection transformer, and the other is basically the query dependent detection transformer. So as you notice, the moment detection transformer that has been proposed earlier does not really do very well on in terms of nicely segregating the positive moments from negative moments, right? So essentially, basically, it says that, hey, this particular frame, if you look at it, well, the difference between the saliency of the positive query and the saliency of the negative query are not very different, right? So they're basically pretty similar. However, if you look at the output from the QD-DETR model, the query dependent detection transformer model, what you observe is that yes, the positive query saliency level is very high here and is also very high here, which corresponds to the frames which are positive in nature for the positive query. Okay, so that's that. So these two problems are both video analytics problems, and they're very related to each other, right? So finding the relevant moments and also finding the relevant highlights or the importance saliency of various clips inside a video. Okay. So in this particular paper, the authors propose this new model, the query dependent detection transformer model, which is basically a detection transformer tailored for this problem, for this MRHD problem, the moment retrieval and highlight detection problem. So the model actually looks like this. The architecture looks like this. You basically have a large video. You break it down into T different clips, and you use some frozen modality specific encoder models as to get representations. So video clip representations and also representation for the query. So the query is also there, text query. You get encoded representations for both of them. Then you use a cross attention transformer module so as to essentially so as to explicitly sort of inject the context of this text query into the video representation. So in this cross attention transformer, you're going to use the videos as queries, and you're going to use the text part as keys and values so as to compute the QK transpose into V, and softmax and so on and so forth, all of that, right? So essentially that gives you video representations which are influenced by the text in the query part. Okay. Now, so once that is done, the cross-attention transformer feeds into the transformer encoder. These are transformer encoder layers, several layers, which basically not just take this attended video representation as input, but also prepends a randomly initialized saliency token. Okay. So now the output of this randomly initialized saliency token is basically what is used for computing saliency score. And saliency score essentially predicts whether this particular video clip is basically a foreground clip or a background clip, in the sense how salient this particular clip is, right? Then you also have a transformer decoder, where the transformer decoder, it's the main idea of the transformer decoder is to essentially take every clip and sort of figure out whether it is foreground or background, and also of course it's another goal is to be able to identify the bound of the moment. So retrieve where the moment starts and ends, right? So that's that. Now, in this particular architecture, the way these models are learned, the way this entire model is learned is using multiple objective functions. I'll talk about the objective functions on the next slide. but one of them is also about being able to recognize positive video comma text pairs from negative video comma text pairs, video comma text query pairs. Right? So therefore, they don't just train on positive, video comma query pairs, text query pairs, but also on the negative ones, irrelevant ones. Okay. The third interesting thing is basically about computing saliency. So input adaptive saliency, for which they basically make use of this saliency token and the saliency score, which basically defines how salient the particular video clip is to the query. Okay. So let's look at into more details now. This is the same architecture that I've copied from the previous slide. The input essentially is a video with L different clips and a text query with N different words. The main objective is to localize the center coordinate MC and with the M sigma within the video. So moment retrieval effectively is about localizing that center of the moment, the moment relevant to the query, and also sigma, the width of the window, around the center, which corresponds to the moment related to the query. Right? Also, the other part is to rank the highlight score for each clip. So the output needs to be twofold. First, the output needs to be the moment, which is represented using two things, MC and M sigma. And also an output expected is that if there are L clips, then for each clip, also tell us the saliency score for each of those clips with respect to the query. Okay. Now, the way that you train this model is using several loss functions. In fact, the total loss is basically what is indicated here. So it basically comprises of the highlight detection loss plus the moment retrieval loss, and then plus some negative loss. So loss corresponding to negative examples, right? And let's basically see what are the components of each of those losses. Okay? And before we look at those components of each of those losses, let me actually talk about how do you compute saliency of a particular clip, right? So the way the saliency is computed is as follows. You have the saliency token, which is randomly initialized, passed to the transformer encoder. And then at the end of it, what you have is basically this representation of the saliency token. Let's call this representation as XS, right? And then similarly, you have these representations for various tokens in the video, and let's call those representations as XVI, right? So the saliency of a particular video clip I is basically given by this formula. So it's basically the similarity of XS with XVI computed by doing these projections, right? Normalized appropriately, where D sort of is the channel dimension of these projected tokens. Okay. Now, the idea is that what is this XS? You can think of XS as the central theme of the video. So therefore, the saliency of a particular clip in the video is basically how close it is to the central theme of the video. You can think of it that way. Okay. So that's that. Now, there are several loss functions that are defined here, and the overall. So if I look at moment retrieval loss function, of course, you will consider the retrieval moment as correct if you could basically get the center correctly and the width correctly, right? So which is what is defined by this part of the loss, which basically looks for M. M is actually a vector. M is basically MC and M sigma combined. So essentially that's M. And you want to ensure that the true M is as close to the predicted M as much as possible, right? So that's the L1 distance. What you also want to do is you can actually also compute the IOU score, the generalized IOU score. So essentially, if you predicted this as the window and the actual window is this, then well, you can actually compute IOU, intersection over union, in that senses, right? And the third component in this moment retrieval score is the cross entropy component. So where for every clip, you have basically identified whether it is a foreground clip or the background clip, and then you can actually take that distribution and compute the cross entropy loss based on the distribution of the real and of the actual and the predicted one. Okay. So this totally defines the overall moment retrieval loss. Now, for highlight detection, well, there are two particular parts to the loss: the margin loss and the ranking based loss. So which is denoted as L cont here, right? So let's talk about the margin loss. So let's say if you have two clips and that one of them is more relevant than the other, let's call the relevant clip as X high and the non-relevant clip as X low. Then what you could do is to ensure that the saliency score that you obtain here for the more relevant clip is actually at least delta greater than the saliency score for any non-relevant clip. Okay, so that's basically is defined as the margin loss. And then there is another loss, which is a ranking based loss. So margin loss is basically between a pair of video clips for a given query, text query, right? But you can also define a ranking based loss, and the ranking based loss is sort of defined here. So given that you have a positive clip and given that you have many negative clips, in fact, capital R negative clips, what you could do is to define this kind of a ranking loss, which basically ensures that you get a very high saliency score for the positive clip compared to multiple negative clips. These negative clips, you see examples of positive and negative clips here. So you could have a positive query here, and then there could be a video clip with high saliency. So query is a kid who watches the screen in the laptop. Well, this particular kid is actually watching the screen in the laptop, so it's a high positive query, or positive query and a high relevant clip, high saliency clip, right? But this is also a clip from the same video. It is a low saliency clip, and then you can actually also combine it with clips from other videos and then say, well, they are low saliency clips in that senses. Okay. So what you want to do is to ensure that you give very high saliency score to this one and low saliency score to this one, such that the difference between them is at least delta. So that's the margin based loss. And then you also want to ensure that this high saliency clip should be ranked much higher compared to all the other negative low saliency clips in the same batch, right? So that basically is taken care of by this ranking loss. So the overall loss, of course, is basically a combination of your margin of your uh, highlight detection loss and margin highlight detection loss and the MR or moment retrieval loss and the negative loss. So essentially, if you also have negative clips associated with any particular query, you also want to ensure that that particular thing is minimized. So the saliency with respect to the saliency is minimized with respect to saliency is minimized between that particular query and a negative clip. Okay, so that's basically how the query dependent detection transformer is trained. So it's actually called as query dependent detection transformer because in the encoder part itself, you ensure that you have the video representation learned in a query dependent manner. So the query sort of influences the way the video representation is computed. Okay. So how does the QD-DETR perform? Well, they evaluate the quality of the QD-DETR model on 3 different data sets: QVHighlights, TVSum, and Charades dataset. So these datasets are meant for different purposes. QVHighlights is for both moment retrieval and highlight detection. TVSum, basically they evaluate for highlight detection. It's basically a video summarization dataset. And then they also evaluate the moment retrieval performance on the Charades dataset. Now, the evaluation is done across several other baseline methods, including the more recent moment deter method, which was also proposed along with the dataset itself, QVHighlights. So the same paper basically puts up moment detection transformer and QVHighlights dataset both, right? So for different other purposes. For each of the 3 datasets, the baselines, some of them are similar, some of them are different baselines, right? So the baselines include input as the video only or video plus audio. So it turns out that the QD-DETR model could also encode audio as well, which are just extra channels which are added, right? And then the accuracy for moment retrieval is measured using these various metrics, right? So essentially, specifically the MAP metric, so mean average precision metric, and also recall. So that's that. Then the highlight detection again is measured using the map metric and the hit at one metric, right? So that's that. Now, highlight detection. So here are highlight detection map scores on TVSum. And what you observe is that whether you look at the QVHighlights or you look at TVSum, the proposed QD-DETR model performs really well. So for TVSum dataset, there are several categories of videos, and you observe that across most of those categories, the QD-DETR model performs best, both in the video and video plus audio setting. Okay. So on the Charades dataset, they use different kinds of features just to compute video representation. So you could use VGG features or C3D features or slow fast and clip embeddings combined, right? And you observe that the proposed QD-DETR model in this particular paper gives you better results, even, I mean, of course, compared to other baselines, but also compared to the state of the art moment detection transformer kind of model. Okay, so that's that. In summary, in this video, I talked about the query-dependent detection transformer model, which basically involves a cross-attention encoder, where the keys and the values come from the text query side, while the queries come from the video side. So this cross-attention helps get a more improved representation for the video, considering the contributions from the text query side. They also included negative pair training, so essentially ensuring that there are negative pairs, negative video comma text query pairs, which are also considered while doing the training. They do multitask training in the sense that they do training for moment retrieval and highlight detection tasks together. And there are several components to this. So they basically have a margin-based loss, they have a ranking-based loss, they also have a cross entropy kind of loss considering foreground and background pixels and clear foreground and background clips. And clearly they also have a moment retrieval loss in terms of identifying the center of the window, center of the moment and the width of the window accurately. Right? To be able to figure out the saliency, they essentially use a saliency token, and that helps them figure out, incorporate the input dependent saliency prediction also as part of the overall loss function for the overall train. The code is available here, and that's it. So hope you like the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.